Okay, so welcome to the RISC-V instruction and assembly tutorial. In this tutorial, I will explain about the RISC-V instruction basics and the assembly of the simple hello world function, because previously I already explained about the how to run the spike and proxy kernel and so on, but I didn't make the video yet about the RISC-V instruction and assembly basics. So this one will explain about the basic instruction and assembly for RISC-V simple program, which we will explain about the hello world program. So let's get into it. First, the RISC-V instruction. We'll see here there is a notation that set less than, and there is some bracket here which has an underscore and immediate. This we can get the instruction from this diagram, from this picture, from this figure. We can see that we can get the instruction from concatenating the underlined letter. In here we have SLT underscore and I underscore again and U. It means that the SLT is one instruction, and there is also SLTI, which is set less than immediate, is one instruction. So there is 1, 2, 3, 4, 5. 5 instruction. 1, 2, 3, 4. So in this notation, we can get that SLT instruction, SLTI, and SLTIU, and SLTU. That's the instruction. And go to the next overview of the RISC-V32I. The RISC-V32I is one of the extension of the RISC-V, but the 32I is the basic instruction architecture that RISC-V has. It is integer computation. It has integer computation, basic integer computation, and by using only this instruction, we can run the full CPU. And in here we have all the instruction in RISC-V32. We have ADDI and ADD and ADDI, subtract, and in this red box, for example, we can know that there is an instruction or an I instruction or I instruction, X or I instruction, and so on. SLL and SLLI, and also we have environment instruction here, abric, equal, and also load store, which will able to load byte or half word or word. And there is also load upper immediate, add upper immediate to PC, and so on. There's control transfer, branch, and jump. There's also CSR instruction to read and clear the instruction byte. You can get here CSRRC will read and clear the bit of the CSR, and CSR S and read and set bit, RRSI with immediate value or register value. So that's it. This is all the instruction of the RISC-V 32-bit. Of course, there is another extension. RISC-V has M or for division and multiplication, but that is out of our scope. We only explain about the basic instruction in here for the 32-bit RISC-V. And there is instruction format. Take a note that this is not the instruction syntax. So this instruction format this instruction format is the format of instruction that RISC-V has in machine language. So for example, we have 0x blah blah blah. And this is the format we have from the LSB 0 to 31, which is 32-bit. First part of 7-bit is the opcode, which is specify the type of instruction format. We have 6 types in here: RISC-V, and G. R is register, and I is immediate, S is store format, and B is branch, and U is upper immediate, and J is jump. As we can see here, after the opcode followed by RD, which is destination, and there is also func3 here, and func7 is 2 fields that defines and specify the operation to be performed. For example, all the R-type instruction will have the same opcode but will have different func3 and func7. So this is what makes them different from each instruction. The opcode may be same, but the func3 and func7 is different. Now we have RS1 is source 1 and RS2 is source 2. Start from 15 to 19 and 20 to 24. And in this and that's how the instruction are decoded. As you can see here, there is also in I type, which is immediate, it has immediate value that use the func7 and RS2. So this instruction will have the three operands, which is destination, right, source, and immediate value. For example, like ADDI, that's it. We will see the kind of instruction after this. And this one is, for example, we have ADDI, which is register type. The syntax is RG, RS1, and RS2. So this value will be in here, and RS1 will be in here, and RS2 will be in here. This is the instruction format for RISC-V. And as we can see here, there are same values of the opcode for branch instruction and same values of the opcode for I instruction, S, and I. And we can see that the place for the destination register will always be the same in the second column, second less significant byte, and RS1 is in the fourth and RS2 in fifth. And the immediate value has different, and immediate value are scattered, but the function tree is the same. Place for function tree is also the same. Sorry for interruption. And here we have immediate value. And for example, here, if we found that this value on a RISC-V binary, what kind of instruction is X067 hex? From here, we can see 7 hex is this one, and this one. Okay, so maybe this one. Okay, so if you can guess what is this, please write in the comment. So if you can guess what is this, write in the comment. And this is the next opcode, which has I, R, and I again, which has another opcode map from RISC-V. And now the RISC-V advantages here is that it has simple decoding format. It has 6 instruction type, and it has 32 non-command fixed length formats. And also there is 3 operand instruction. 1 is destination register and 2 source register, and no need to extra move to preserve destination operand. So if we have ADD X2, X3, X4, if we want to add if we want to preserve X4 or X3, we have the third operand that will save the result, and we can preserve both of the register and we can preserve this both register without changing the value. Now the other advantage is that all instructions have the same RD, RS1, and RS2 location. As we can see before, the place for RD, RS1 is the same, so that register access can be gained before decoding the instruction. Without decoding, the CPU will already know the place for RS1, RS2, and RD. And the immediate field is always sign extend, and the sign bit is always in the MSB of the instruction, so the immediate can also proceed before decoding the instruction. Now we move to the RISC-V register. In here, 32-bit register length is 32. In here, in the RISC-V 32-bit, the length is 32, and we have X0, which we call it 0. It is a hardwired 0 register with a length of 32-bit. And there is also return address register X1, X2, and so on. We will call it by the name of ABI name, which is return RASP stack pointer. There is also global pointer, thread pointer, temporary, and save register, and then also function argument or egg function argument, and return value will be written on the A0 and A1, and also save register will be on X18, S2, and also there is separate save register which used for frame pointer, and that's all. And also another temporary register. We also have PC register, which is not modifiable. And of course, what if there's question? What if the function has more than 8 arguments? We will pass it to the stack. That's right. If the function argument is more than this, then we need to pass it to the stack and save there. Now for the RISC-V instruction, we have integer computation here, ADDI, sub, and NI, or I, SOR, SORI, and so on, SSL, SSLI, SRA, shift right, shift left, and load, set program counter, shift left, set less than, and load store, conditional brand, jump, and other instruction for CSR, environment, and events instruction. In summary, the feature of this RISC-V and the characteristic is that it has 32-bit byte addressable space, and all instruction is 32-bit long, and it has 31 register, and all is 32 byte wide, and register 0 is hardwired to 0. All instruction perform between registers, so no memory instruction. All of instruction needs to be put, all of the computation and instruction is performed by the register. And there is safe load instruction for word, half byte, and half unsigned, byte unsigned. Immediate option for all arithmetic, logical, and safe instruction. And there is always, and the immediate is always sign extend. And we have one data addressing method using register and immediate offset, and also the program counter relative branching. And there is no multiplication and division instruction because it is on the other extension of the RISC-V, which is RISC-V 32M. But without multiplication and division, we can run the multiplication by extended instruction, by expanding by what? By make use of the current instruction. So without multiplication and division instruction, RISC-V 32I can make use of the current instruction to perform multiplication and division. And there is 2 instructions for 32-bit constant configuration. So for if we have 32-bit constant, we will load the first upper of MSB, and this is the first, and then we load the LSB using ADDI, and this is LSB. Okay, that's it. Now we move to the program translation step. Usually in logical step, the first C program will be compiled by GCC or anything clang or so on, which is contain main, and it will compile into an assembly program. So the text blah 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 on instruction, this is already assembly language, will be assembled into the machine language module, which is contain O, and the library will be assembled into object program, and then the linker like LD or LLVM linker, will create the executable or elf that is called a.out, and then it will be loaded. So the above are Unix suffix name. It is equivalent on Microsoft as .c, ASM, obj, lib, and x. Now there are helpful RISC-V assembly feature. For symbolic register name, we have A0 until A7 for argument register, which is actually X10 to X17, which is hard to remember. And there is also X0 for X0, which is hardwired to 0. And we have pseudo instruction, which is the shorthand syntax for most common assembly idioms. We have move, destination, and source, which is actually the ADDI, RD, RS, and 0. There is also load immediate 13 to RD, which is actually ADDI, RD, X0, and 13. So plus just will put in here. That's it. Now for the symbolic register name. We have here the list of the register. This is the floating point register. We'll not talk about it in here. And there is name of the register using X, which hardware understand, and this is more friendly to us. 0, RA, SP, and GP, TP, and so on. Now, not all of this register is preserved across call. So when we have this register like S0 or function argument, it is different. So the callee needs to save it for the caller. And because it should be preserved across calls, so if a function like if you have main and call print, the S0 value in here should be the same with S0 after print. So this print needs to save this register and restore it again after function call. So S0 is preserved across call, but it is different for function argument, which should be saved by the caller. So if we have main and print, for example, in main we have a 0 value of something like maybe 1. Before entering the print, the main need to save this register, and then because after calling the print, the A0 will be different from previously. So that's why it is called caller save register, which is need to be saved by the caller. And this one is callee save register, which should be saved by or maintained by the callee, a function that is called, because one is preserved across call and one is not. Okay, so next is the pseudo instruction of the RISC-V. Pseudo instruction is the common code instruction. For example, we have NOP, which is actually in reality the RISC-V will translate into ADD. The compiler will translate into ADDI, X0, 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 and X00, and so on. These are the sample. I think we only need to care about this one, but if you want to analyze more, you can look up into this table. And these are the instruction that is not using X0, load address and store global and so on. Here has load immediate. And there are 6 general stages in calling function. First is to place the argument where the function can access. The second is to jump to the function. After we place the argument, let's make an example here. For example, we have main printf. We place the argument for the printf. Next, on the next slide, we will talk about this. Place the argument first on the register that the function will access, and we jump to the function using JAL. So JAL printf or call printf, and then we acquire the local storage resource, which is allocate the stack frame for the function and save the register that we require to save, and then perform the task of the function, and then place the function result value, return value, to where the calling program can access it. We restore all the register that we changed, and we release the local storage resource, which is stack frame, and then we return control to the point of the origin using read. So in and out here. Now the RISC-V function call convention. The register are faster than the memory, so we can use them. For example, here A0 to A7 is 8 argument register to pass parameter, and we have 2 return values that can be used by using A0 and A1. RA itself is 1 return address register to return to the point of origin. Now there is function prologue and epilogue. Function prologue is located before the task of the function is run. So after main calling the printf. So in printf, this is prologue and this is epilogue, and this is the printf function. Each time a function calling another function, each time at the prologue of the function, there is ADDI SPSP minus frame size. What is this? It will allocate the space for stack frame by adjusting the stack pointer, which is SP register, and it will save the value of RA to the stack, save return address to the stack, and save other register if needed. And now the body of the function, and after that, restore register from stack init. Let's make some figure here. For example, now the stack is SP is in here, which is 32. For example, this is 45. Now the stack in here and in here, and then we run to this ADDI. SP is the value of SP is the current SP minus frame size. For example, frame size is 16. So current SP is minus 16. Now the stack pointer will move to 16 because it moves in here and store the return address to frame size, which is 16 minus 4 to 12 SP to 12 SP. So this is SP 16 plus 12 around here. That's right, 28 on 28. Now there is array here, which is 4 byte. There is return address in here. Now this is the stack frame, and it can be more if there is other register to save. But now the body of the function run, and then program function is run, and after function finish, it should restore the register from stack if needed. For example, here we load again the frame size, which is 16 minus 4, again 12 SP to the RA again. So this one is loaded to RA. Now RA may be changed, but it will now become the default value, and then ADDI SPSP frame size, which return the value of SP. Current SP 16, frame size is 16, so SP jump back to here again. Now the SP is 32, and this is no longer stack frame. And then return. When return is called, the A0 will be passed to the caller. Now let's try the hello world example. In here we have include stdio and we have main. We can see here in main function we call the printf hello and followed by the word string. This will be placed on A0 register, and the second argument will be saved on A1 register. And then after that we return with 0 value, which should be, we need to set the A0 register because that's the return value. Okay, now there is instruction that we will use in here: add immediate, store word, load upper immediate, load word, load immediate, call, return jump, and add upper immediate. ADDI is a simple sign string immediate to add operation to RS1. So this one is plus and save to the RD. Store word is storing the value of RS2 to memory that pointed by RS1 plus offset. This is store type. And load upper immediate is load the immediate value to RD, but the MSB because it is shifted 12-bit to RD, so the lower 12-bit is 0. And load word is load the value. Load word is load the value from memory RS1 plus offset into the RD, and load immediate will load the value of content into the RD, which actually it expand to load upper immediate followed by ADDI or not. It will use the few instruction as possible, and is call RD symbol. It will write the address of next instruction PC to RD, then set the PC to symbol. So it will expand to AUI PC RD, offset high, then JAL to offset low. If RD is empty, X1 is assumed. And return will expand to jump and link register X0, 0, and X1. Jump and link register itself will set the PC to RS1 and extend offset and masking of the LSB of computed address and read the previous PC4 to RD. If RD is empty, X1 is assumed. And also there is add upper immediate, same with LUE, but this is for like LUE but add to, which is specialized for program counter. We can see more at the RISC-V reader book in RISC-V instruction listing. All of this presentation is compiled from this book. Now in Hello World in assembly, we have .text, which is the assembly directive for that. Show that the assembler, oh, this is the text region. text section. The code is in here until there is another section like read only data. So in this part is code and this is data. Why data? In here we have the align to, which is align code to 4 bytes, and global main, which declare the symbol that main function is in here. Main is the label for main function. And then we see here, this is the prologue. We allocate stack frame like before, 16, and then store word return address to 12. Let's make a figure again. Usually it is the same figure. I will make it same. For example, stack pointer is here. Actually, here is 0x f and so on. We modify the s stack pointer and move it to here to lower bytes to 16, and then we store RA to 28 in here. Now we have some space in here, but it is not used. So after that, after the stack, after the RA is saved, save the return address, we load upper immediate with high value of the string1 address. So string1 is in data, which is section read only data, and it is aligned to 4 bytes also. So string1 is have address, and we load the upper part, load upper immediate 12-bit, and then to A0, and then ADDI the current A0 with the lowest part of the string1. So now the A0 contains the address of string1. And then also for the same for the A1, height of string2 and low for string2. Now the A1 value pointing to this string2. Now after that, we call the printf. Printf will read the register A0 and A1 as first and second arguments. So it will print this one A0 and this is A1. Okay, this is A0, A1. I will print that. Then after that, go out and then we load the RA, previous RA to current register. We load this one and then we deallocate the stack frame and move again the stack to here. Now this is already unused. And also we load immediate to A0. Just set the A0 to 0 because we will return 0. After that, finish and return. Return will return to the caller and the program will finish. That's all for the assembly hello world. Now this is the machine language. Usually before linking, the hello will be like this. The address is 0 like this. This is not defined yet because there is no information about the part of the data. And after linking, it will print like this and the address is fixed. And there is statically string1 and string2 is already defined, so the linker will add the value to the previously undefined value. So this is the final hello.out that can be executed because the symbol table include in the object file record, and object file record the label and address of all instructions to be edited by the linker. So now the memory layout that we talked about before. This is the stack. For example, here highest address is at the top and this is the lowest address. Stack will grow here and dynamic data will grow up. And we have stack pointer starting from BFF0, and there is also text section that start from this because this is reserved. So the text start from 10,000 hex, and the program code and constant is saved in here. Code constant, and there is statically linked library. And the static data after the text, located after the text, start at 1 million hex, right? 10 million hex. It contains global and static variable, and after that there is a dynamic data which is a malloc on program. Yes, here malloc is called heap or dynamic data, and it grows toward the stack. It also includes the dynamic link library. So that's it. If there is any other question, so that's for the RISC-V instruction and assembly information that I can explain. That's just the basics. So if you have any question, you can write in the comments. Thank you.